So question 24 is probably the only insightful question in the 2025 AMC 10A. However, so when I look at a question like this, let's read it first. Call a positive integer fair if no digit is used more than once, it has no zeros, and no digit is adjacent to two greater digits. For example, 196, 23, and 12463 are fair, but 1546 is not because 4 is adjacent to 5 and 6, which is each of them are greater than 4. Same with so 320 because 0 is used, and 34321 because 3 is used 2 times. Right? So how many fair positive integers are there? How many fair positive integers are there? So in questions like this, I personally normally look at two possible approaches that might apply. So let me write those here. So one possible approach in questions like these is that take each selection of digits, say we're looking at a 4-digit number, and develop a pattern of how many possibilities exist for 4 digits, for 5 digits, 6 digits, so on and so forth. The other option is where we start small or big, doesn't matter. And let's say we start with 2-digit numbers, right? We figure out how many possibilities exist, right? Call the number xy, how many possibilities exist, and then we try to add a third digit, call it z, and see if there's a certain pattern that emerges upon adding a digit, right? So z added to a 2-digit number gives a certain number of possibilities. We'll see if there's a pattern, a recursive pattern that can be developed from that to that. And then we'll see if that pattern holds when we add a 4th digit, w, right? Now, thinking about this question, approach number 2 will be a little tricky because let's take an example. Let's say that we are doing using the numbers 45, right? 4 and 5. So we have the number 45, which is a fair integer, right? Now, if I add another number here, it depends whether the number that I'm adding is going to be on this side or that side, right? Because if, let's say I add the number 2. So 2 would be required to be on either end because the smallest number in a sequence cannot be anywhere but the outer ends, right? On the flip side, if I add the number 9, then 9 can go here, 9 can go here as well in the middle, right? So 4 in that case becomes the smallest digit, and we have to make sure that 4 stays on either end of the number. So that's what tells me that approach number 2 is going to be a little complicated. So I'm going to start with, let's say, 1-digit number, 0 cannot be used. So essentially, there are 9 possibilities. If I look at 2-digit numbers, right? So from 10 to 19, I cannot use 0, and the number and any digit cannot be repeated. So that excludes 10 and 11. So that gives me 8 possibilities. And if we take it further, we'll see that 20 to 29 also has 8 possibilities, all the way 90 to 99 has 8 possibilities, right? So total possibilities here is 72. Okay, so far I don't see a pattern 9 and 72. I don't know what that pattern could be. So let's try to figure out with 3 digits. So 3 digits, let's use the numbers 2, 3, and 4, so 234. but it's not that complicated. So we're going to try and manually write down the number of pair numbers that is possible. So we got, using 2, 3, and 4, we have 234, 243, 342, 432. So 2 has to be at the ends, and then the other numbers would be either in the beginning or the end and flipped. So we have 4 possibilities here, right? So now I'm kind of trying to sense a pattern here because 4 is 2 squared, right? We'll see. It's too early to call. Now let's do 4 digits. Let's again use 2, 3, 4, and 5. So let's try to manually write it out. So 2, 3, 4, 5. So 2 has to be in the beginning or the end. So let's finish writing all the numbers with 2 in the beginning. So we got 2, 4, 5, 3, 2, 3, 5, 4. I believe that is it because 3 cannot be in the middle. So 2, 3, 4, 5, 2, 4, 5, 3, 2. Oh, there's one more. 2, 5, 4, 3. Right? And essentially, I don't have to manually write it out. If I move 2 to the end, essentially it's going to be the same set of numbers. So 3, 4, 5, and then 2 at the end. 4, 5, 3, 2 at the end. 3, 5, 4, 2 at the end. Same thing here. 5, 4, 3, 2 at the end. Right? So 8 possibilities here, which is 2 cubed. Okay, so now I see a pattern developing, but which is 2 to the power n minus 1. This is, yeah, it looks like 2 to the power n minus 1. But then we have chosen 2, 3, and 4. So overall possibilities here would be 9 choose 2 times 2 squared, right? This would be 9 choose 3 times 2 squared. 9 choose 4 times 2 cubed, right? So if I now try to build my sum, that is 9 plus 72 plus 9 choose 3 times 2 squared plus 9 choose 4 times 2 cubed plus dot dot dot, it's going to go to 9 choose 9 times 2 to the 8, right? Now, looking at this pattern, my hypothesis is that this is likely going to be equal to 9 choose 2 times 2, going by this pattern, right? And if we look at that, it is exactly 72. 9 choose 2 times 2 is going to be equal to 72. And this should be equal to 9 choose 1 times 2 to the power 0, which is 9. So now we get a nice pattern. S is equal to 9 choose 1 times 2 to the 0 plus 9 choose 2 times 2 to the 1 plus 9 choose 3, 2 squared plus dot dot dot, 9 choose 9 times 2 to the 8, right? Now this pattern becomes even better if I multiply with 2 on either side. So this is equal to S. So my 2S becomes 9 choose 1 times 2 to the 1, 9 choose 2 times 2 squared, etc., dot dot dot, 9 choose 9 times 2 to the 9. So this lends itself very nicely into, this is equal to 1 plus 2 to the 9th minus 9 choose 0, which is 1. So this is 3 to the 9th minus 1. So my sum will be 3 to the 9th minus 1 divided by 2. Right? So if we solve this, we will see that we get the answer to be 9841. Now there is one other way without having to do the entire calculation and get to 9841. So if we break this down, we get 3 to the fourth so this becomes 81 squared times 3 minus 1 over 2, right? The reason I wrote it this way is to come up with a nice units digit. So 81 squared is going to be ending in 1, times 3 is going to be ending in 3, minus 1 is going to be ending in 2. So when I divide by 2, that's going to be ending in 1, right? So I need a number that ends in 1, which essentially, I know it's not going to be 511, that's too small. So it's either 9841 or 17711. But I know that 81 squared is roughly 6400. 6400 at times 3 is roughly 19,000. 19,000 minus 1 is almost equal to 19,000 divided by 2 is going to be roughly 9,500. So I need a number that is close to 9,500 and ends in 1, which gives me 9841. I mean, that's just a small nuance at the end. We don't need to do that. If we just run the calculation really quick, we can get to 9841. So the answer for this is C. So again, it's a little more interesting question, solution strategy to be developed. Now this is question number 24. By this time we are probably trying to rush to finish the job. Otherwise there is a slightly more methodical way to come up with this pattern, but it's in the crunch time it doesn't always occur to us. So what I wanted to demonstrate is that proceeding by just writing stuff down and try to develop a pattern seems to work many times in the AMC 10. Right? In AIME, you'll have more time, and the questions will require a great deal of more thought.